we have sort of what is referred to as, we talked about, the mass defect. Mass defect, again, is a slight difference in sort of the mass of really sort of what makes up the nucleus, your protons and your neutrons, and really sort of the mass of that particular isotope would be. And that slight difference is sort of what will be converted into energy via sort of, we saw kind of really two ways to do it. They're really both based on sort of E equals mc squared. And again, two common units of nuclear binding energy, joules per nucleon or mega electron volts per nucleon. And they both can be used, again, as a measure of stability. Again, the higher your number for your binding energy per nucleon, the more stable that isotope is. And then obviously vice versa, the lower the number that you got there, it would be obviously less stable. Any questions on those guys that we talked about before here? Okay, so we got one more of these type of examples, I think. Let's take a look here. All right, calculate the binding energy per nucleon. And again, let's do both just to make sure. Mega electron volts per nucleon and joules per nucleon here. And of iron 56 there, and iron is number 26 on the periodic table. And a couple of those numbers there that we used before, we have our proton 1.00783 AMU and our neutron at 1.00866 AMU. All right, take a few minutes, see what you come up with, and then we will discuss. So let's take a look here. So we are dealing iron 56. So we got iron 56. Again, go into the periodic table there. We can find the atomic number there for iron, which is 26. That's going to tell us that obviously we then have 26 protons. In terms of neutrons, again, mass number minus atomic number going to give us 30 neutrons. That's important, again, for our mass defect. So that's what we could calculate here up front. So our mass defect going to be our 26 protons times our 1.00783 AMU plus our 30 neutrons times 1.00866 AMU. And that's going to be subtracted from, again, the mass of the isotope, which in this case is 55.93494 AMU. That is going to yield us a mass defect of looks like 5284 0.5. So the process of what is sometimes referred to as nuclear transmutation is really when we sort of shoot a particle at something and it becomes unstable. And one way we could do that is to sort of use something like a particle accelerator, like is pictured here, and basically put the particle in, and it kind of magnetic field, electrical field, spinning, and then you can basically target it at a particular isotope. This may be like when you bombard something, it may become very unstable and not very happy and go through sort of fission sort of reactions. So this is a way that you can sort of do processes where you produce some unstable sort of elements or make things unstable that they will go through a fission reaction. So this is what sometimes referred to as transmutation. So again, you kind of have like perhaps a stable guy, you shoot like a particle at it, becomes kind of unstable at that point, and then we'll kind of split off, maybe go through that sort of fission reaction and give off some particles and stuff like that. Here's a transmutation, transuranium elements, and again, in each of these we see sort of a particles sort of being shot at it for the most part. And again, it's going to produce a lot of these sort of elements that are sort of like on the bottom there of the periodic table, those bottom two rows, the lanthanides and actinides series, where we have a lot of radioactive guys on the bottom part there. And that's where we see our americium, our like berkelium, californium, or einsteinium. Again, these all can be produced sort of through these sort of processes where we basically hit them with some particles and produce these sort of new elements, if you will, these sort of radioactive sort of elements. And that's sort of how their sort of man-made elements are sort of produced, is through this process here. You basically bombard it with a particle, it becomes a little upset about it, and then goes through this sort of process where it splits. And that's what is happening here with nuclear fission. And this is an example of a nuclear fission reaction. And what we get here is we have a neutron, for example, here hitting uranium-235 sort of a nucleus, kind of stable at this point, becomes unstable like a bowling pin here, and then basically will kind of split off into some new nucleuses and also produce a bunch of neutrons along the way. As we'll talk about in just a second, is part of the process here where obviously if we could initiate this process by a neutron and we produce neutrons, this could kind of keep this process kind of going and going and going. Overall, again, if we sort of do a comparison in terms of the energy that is here versus, say, the energy for a ton of coal, we see that we get about, if we take kind of our products minus our reactants here in terms of energy, we get a energy difference there that's being released by uranium-235 of about 10 to the 13 joules per mole. And in comparison to a ton of coal, it's going to give off 10 to the 7 joules. And that's a much bigger difference in terms of the energy that's happening there. And by the way, this is Einstein's equation. This is E is equal to mc squared. The m here is the mass defect. And just to give you an idea, in this case, what we're doing is, excuse me, the difference between really our sort of reactants and products, right? So the mass difference here and the mass difference here is how we get the mass difference, kind of products minus reactants. You could do it that way as well. And, it gives you the sort of the mass defect in an equation sort of like this. So if you have an equation like this, and you want to kind of calculate binding energy or energy like that, you could kind of do, the difference in the mass of your products and your reactants times c squared, and you can use that as your mass defect. Why do they compare these two things? The reason they compare these two things is uranium is sort of used in nuclear power and like a nuclear power plant, while coal is burned in a traditional kind of power plant as obviously a source of power, and we use for electricity and stuff like that. So you can see you got a lot more energy out using sort of the fission reaction versus say the coal reaction. We'll talk about some benefits and maybe some non-benefits of these things as well. Sorry, all my equations here are all kind of messed up. I think they should be okay on your paper, so that's good at least. We'll do that there. And this 54 is way out of there. So that 38 should go there. So let's cross that out already. 235 or uranium, 92 plus 1 over N. So this again is that sort of fission reaction that was taking place. And what we see here is a typical sort of fission reaction. In this case actually is being started sort of by this neutron coming over and attacking that uranium, making it unstable. And it splits off into these two nucleuses here. Now, it should be noted that it may not always split off into those two. You may get some other ones along the way. And sort of our fission products, as you can see here, for the most part in this sort of area of mass numbers, typically, sort of what we get sort of produced as a result of that. So you won't always in this sort of reaction get, say, strontium and xenon. You may get some other products that are formed as a result of this sort of reaction. And that's sort of those two peaks, sort of where we typically would see a majority of those sort of products being formed. Again, as we talked about, sort of what will kind of keep this reaction going in some cases is this production of neutrons, which then can kind of go back around and start this reaction going. Also, every time this reaction sort of takes place, there's a discharge of a good amount of energy that's happening, and obviously some radioactive sort of products. So keeping this reaction going is what is sometimes referred to as a chain reaction. A nuclear chain reaction is basically a self-sustaining sequence of fission reactions that occur. And as I mentioned before, the reason it could kind of do that is because sort of what starts it all off is that neutron, right? And if it then produces, in addition to other guys, more neutrons, again, you have these neutrons that can kind of come back around and start the whole reaction kind of over and over again. So as a result of the reaction, you're actually producing sort of the thing that initiates it and can keep it going, going, and going. What else is sort of needed to keep this reaction sort of self-sustained? You need to have what is referred to as the critical mass of something like uranium or fissionable type of material, enough material there to, kind of keep this reaction kind of going and going along the way. And that's what we see here in this sort of situation. If we have it at critical mass, what we have is plenty of material to keep this reaction going. Every time it splits off, we get more neutrons, which then can go on and attack more of the original guys, splitting off, giving us more neutrons and more attacking. And everywhere along the way, it sort of grows sort of exponentially. And we're producing these neutrons, and we're also producing everywhere along the way there a lot of stuff, including obviously energy being produced. In addition, we're producing new nucleuses that could also be very radioactive as well, and it kind of builds and builds and builds. If we keep it sort of non-critical, you could kind of keep this reaction under control where it really won't sort of grow super exponentially. You kind of keep it sort of not so big in terms of how it grows. Now, this is obviously how sort of like I say nuclear sort of bomb sort of works. For example, they have subcritical mass of uranium-235 on both ends, kind of the triangle and the triangle hole there. When obviously this thing hits, it has some explosive, which is going to send a little wedge, if you will, and kind of complete it. When you complete it, then you obviously have now made a critical mass of uranium-235. Obviously, that's going to kick off this sort of uncontrollable sort of reaction. And obviously, it will continue to grow and grow. Lots of energy, and a lot of times as well, obviously, a lot of byproducts that are produced that are very much radioactive and radioactive emitters along the way, which is never sort of a good thing. Now, we could also use sort of this fission reaction to power, say, like a nuclear reactor for, say, nuclear power. And really, when we think about sort of energy plants and stuff like that, there's sort of the traditional energy plants and kind of the nuclear energy plants. If we take out, wind power and all that kind of stuff. But in a sort of a nuclear power plant versus, say, a traditional power plant, there really is no difference in terms of, for example, how it sort of works. And what I mean by that is, they both, for the most part, have water. And for the most part, you heat the water. When you heat the water, you obviously create steam. Steam goes out to like the turbines, to the generators, and you get some lights, right? Which is good. Lights turn on. Also, obviously, if you condense down, go through condensation, right? Condense down that steam, you get the water and get this nice sort of cycle in terms of how sort of power is sort of generated. Now, the real main difference in terms of what's going on in, let's say, a traditional versus a nuclear power plant is this part right here is kind of like how you heat the water. In a traditional power plant, we burn coal, which is why there was that comparison on the previous slide between sort of uranium-235 and sort of coal. You burn the coal, the heat from the burning of the coal basically heats up the water, you get your steam and all that good stuff. The difference, though, in a nuclear power plant is they use a fission reaction to basically heat up the water. And they have what are referred to as fuel rods. And inside these fuel rods are kind of like little eraser size pellets, basically, of uranium 235, for example. And basically, that is where sort of the nuclear part of the reaction takes place. As you can see, it's usually shielded, usually as well, right? These things are big shielded in these big domes, for example. So if you're driven down the 5 freeway there in San Onofre, right, there's those 2 big domes right there by the water, and there's San Onofre power plant over there, and that's where, you know, sort of all this sort of process is sort of happening here. So in here we have basically the fission reaction that occurs where we have sort of an insulated sort of container that contains water. The heat from this reaction is going to heat up this water, which is in another tank of water. And the heat that's coming off, obviously, in this sort of sealed container is going to be used to make the steam, which goes out to the turbines, obviously, and out to the generators and all that good stuff. Also, again, through sort of condensation process or cooling it back down, you get sort of that reuse of that water kind of going in and out, which allows it to kind of regenerate itself. Usually need a lot of water, which is a lot of times why these guys, like the one in San Onofre, are located near water sources. Or if they're like inland, they usually have very, very big water towers and stuff like that to allow sort of this process to sort of continuously occur. Now, why does this reaction not go sort of crazy and stuff like that, you know, and become sort of like a chain reaction? And it doesn't become a chain reaction because of a couple of things. First off, they keep the mass below critical. So first off, they have sort of less than critical mass of uranium there, which means if this reaction sort of went off, they could kind of be controlled. They shouldn't be self-sustaining and continuously processing and processing. The other important thing that they have in there to kind of keep it under control is actually things known as control rods. And these control rods, for example, are dipped in things like cadmium or something like that. And these things are really good neutron absorbers. So why would sort of neutron absorbers be really important in this sort of process? And why would it be able to sort of keep it under control? It's able to keep it under control because if you think about what kicks off this reaction, it's a neutron. And what is formed as a result of this reaction, in addition to other things, are neutrons, which, as we talked about, can come back around really and sort of initiate this reaction to occur again. But by having these control rods, what they essentially do is kind of take out a lot of the neutrons and leave only a few neutrons there, again, allowing you some control over how sustainable this reaction is, how sort of fast this reaction sort of occurs and stuff like that. So you have these sort of control rods that are in there, these uranium rods, which have the fuel rods. And like I said, pretty much all the radioactive part over here sort of shielded, if you will. And again, the sort of non-radioactive part-ish sort of happening here to heat this sort of water over here. Any questions on that there? So some people will say, you know, this is sort of cleanish energy because, you know, you're not burning coal and stuff like that. And obviously there is, you know, depending on what you look at as to what you think about in terms of is it cleaner or not cleaner. It's cleaner in the sense that you're not directly burning coal, which obviously contributes to tons and tons of sort of pollutants in the air. But on the other hand, it does make a lot of nuclear waste, right? And it makes a lot of nuclear waste of things that obviously, as we will see here in just a second, pretty much can hang around for a very, very long time. And it makes a lot of products that basically will be around for a very long period of time. And you have to think to yourself, well, you know, who controls those things? Where do you put those things? How do you store those things? And those were a lot of issues for a lot of years. And really, for a lot of years, a lot of these nuclear power plants actually just kind of stored all the waste sort of in house and in site because nobody wanted it shipped anywhere, right? People didn't want to go through their neighborhoods and stuff like that. So I believe a number of years ago, at this point, I think in Nevada, I think they built a big sort of receptacle site for a lot of these sort of products and stuff like that. And I think they've now started using it within their last years and stuff like that. Um, but before that, you know, a lot of these guys would sort of keep all this stuff sort of in house and not want it. People didn't want it sort of shipped sort of through their neighborhoods and stuff like that. Also, a lot of the nuclear power plants, you know, are sort of offline, a lot of them, because it's a lot of maintenance and updating that needs to be done to a lot of our sort of nuclear power plants. So one, again, sort of negative aspect of it, obviously, is they both obviously create some type of waste. The other aspect of it is nuclear fission, for example, as I mentioned, creates a lot of radioactive, what is sometimes referred to as spent fuel. Spent fuel are basically the products that you get as a result of that sort of fission reaction. So remember, you're starting this reaction with some uranium, like 235, for example, and it's going to go through that fission reaction. It's going to produce some products, right? And although these products may not be used directly in sort of the fission reaction for heating the water, and the neutrons are going to come back around and stuff like that, but you're still producing a lot of these guys that have very, very long sort of half lives and stuff like that. And how long you need to store them before they're not such a hazard. And you can see that, you know, there's a lot of things that are relatively high in terms of hazards. If you just kind of go down in terms of years, you know, you're in this region, and that's like 100 years to, you know, 1,000 years. So a lot of these things, you know, do hang around a very long time. In order for something to be, you know, considered not such a hazard, you're in this area, which means for a majority of things, you still have a great number of years before these things are not so bad. And so that brings up again a lot of situations like, what do you do with them, how you store them, who keeps track of them over all these years. Any question on fission? Now we're going to talk about fusion here, which is a little bit different than fission. And fission is where we sort of split off one guy into multiple sort of reactions. In fusion, what happens is we actually take two smaller nuclei, and I'll rewrite these again. I think it's okay on your handout. And we take two smaller guys to produce sort of a larger nucleus, putting them together. And again, a couple of the other ones that are there, a couple of hydrogens here, then produces a helium, and then our lithium plus a hydrogen, producing a couple of our alpha particles and stuff like that. But it gives off a lot of energy, as you can see here. This guy goes that way, this guy goes that way, and this guy kind of goes this way. And this occurs at very, very high temperatures, like the sun in this picture here to the right type temperatures. So when we talk about fusion, it happens at very, very high temperatures. And again, fission obviously happens at normal sort of temperatures. And again, fission breaking things apart into kind of smaller nuclei and two or more nuclei, fusion putting two small guys together to make sort of a larger nucleus under very, very high temperatures. Now, when we use sort of isotopes, we can use them in medicine for a variety of sort of uses. Obviously, when we would choose something for medicine, we would want to make sure that, it does have a half-life that is, very small usually. We typically wouldn't want to use something that has half-life of years and stuff like that, as obviously the follow-up appointment would be very, very far down the road. So here are some examples of some isotopes that are used for a variety of things over the years. Sodium 24 there is a blood flow tracer, iodine 131 for your thyroid, um, fluorine 18, positron emission, and technetium 99, imaging agent. Can these things be used? Why are they helpful? Well, they can be used and helpful for a couple of reasons, but one couple of reasons are a radioactive isotope of an element basically will sort of behave the exact same way as sort of a non-radioactive isotope, if you will, in your body. And what that means is, if you have sort of the advantage in that sense of the radioactivity, is you could kind of follow the radioactivity throughout your body through, say, imaging and stuff like that, and sort of seeing where things are. They sort of highlight, if you will, like the scans that we see here. It will sort of highlight. You can follow the radioactivity, you can get some X-rays and stuff like that, and really sort of see, maybe where it's getting into and stuff like that in your body. You could also use radioactive isotopes. They used it years ago as well, and still do, I think, as well, in little cases. To kind of use it to kind of shrink tumors and stuff like that. They would sort of implant them into tumors in an effort to sort of shrink them down and stuff like that. So it can be used a lot. Obviously, we would want something with a smaller half-life. And again, here you can see on the right there, sort of a bone scan using technetium 99. And again, it just sort of highlights certain things within, say, your body like that you could just kind of look at and obviously analyze. Has a half-life of 6 hours. So, really about after 10 half-lives, most things are fairly gone at that point. So obviously, within a few days or so, it's pretty much going to be gone. One way that we sort of follow and keep track of radioactivity, especially if we're working with it, as we talked about a little bit earlier in this chapter, if you are working with something that's radioactive, it's really important to understand the safety precautions that you need when you're working with something like that, and also what type of emitter it is. So as we saw before, there is a big difference in terms of, say, an alpha, beta, and a gamma sort of emitter in terms of how far, say, something penetrates in your tissue of your body and stuff like that. Remember, gamma goes pretty far, alpha not so far, and stuff like that. So those different layers of protection that you may need, as we talked about, you may just need some gloves, coat, and stuff like that. You may need some lead and some shielding and some heavy duty sort of protection, depending on sort of what you're using. A Geiger counter also helps us sort of look for sort of radioactive things. And typically when we use sort of radioactive isotopes and stuff like that, for example, in the lab, you usually go around after you're done working with the Geiger counter just to make sure, you know, you didn't contaminate the lab that you're working in, or the area is relatively clean. So you basically, it's a wand. It has usually a little dial, and also usually a sort of audible sort of sound that kind of beep, beep, beep. And if you hear a lot more beeping, 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 that usually is something that, is fairly radioactive and stuff like that. Um, would you hear some sound if you just held this up sort of in by itself, really not near anything? And the answer is yeah, there's some background radiation, right? So we're exposed to sort of radioactive sort of particles, in our everyday life. So there is sort of a background radiation, but if you held it up and you heard it beep, 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 that's clearly not background radiation and stuff like that. Always good to kind of scan the area after you're done and clean up, and obviously good to scan yourself as well to make sure obviously nothing hopefully is beeping. Your shoes as well is a very common thing. People don't realize they step on things when they're working in the lab, and you don't want to walk around with contaminated stuff. In addition, a lot of times we were doing a lot of radioactive work. They used to, when I did it as well, they used to make you wear like a ring and a badge and stuff like that. And and every so often they would sort of develop it and see how much you've been sort of exposed to, based on, it used to be film and stuff like that. I'm not sure what they use these days for that. There is sort of biological effects in terms of radiation, and it is based on sort of the type of, again, radiation that we're sort of exposed to, as to sort of the factor by which we would sort of multiply these things. There's what's known as a RAD, which is a radiation absorbed dose, and there's sort of a REM, which is sort of the equivalent for men and stuff like that. And for example, here in this table, you could just see some things that, you know, we get exposed to, you know, X-rays, medical, air travel, nuclear waste, if you happen to live near where they test weapons, I guess, as well. You know, depending on sort of where you're at as to what you're exposed to. But sort of the quality factor, which is basically a RAD times Q, and you can see that, you know, depending on the type of particle, we have a much lower quality factor. So that's a 1, which means, again, this is going to penetrate a lot more. This doesn't penetrate as much, so you technically could be exposed to a little bit more of that without maybe some substantial damage. Obviously, when you're working with anything that's radioactive, there's many things that you should do, but one really important thing, in addition to obviously all the safeguards and stuff like that, is usually like limit your time of exposure. Yeah, so you don't want to be standing over something that's radioactive nonstop for hours and hours and at a time and stuff like that. So limiting that sort of exposure is also a very big thing, obviously, for safety and stuff like that. Any questions on that there? That should then wrap up our nuclear chemistry chapter here. Any questions on any of that nuclear chemistry stuff? So we're just going to hit some of the highlights of organic chemistry, a little survey of some of the functional groups, and a little bit how naming some simple sort of organic compounds. And hopefully, if you're going to continue on to organic after this, it'll hopefully give you a good idea maybe of some of the stuff that maybe you might be encountering. So let us talk about some of this here. So organic chemistry, pretty much any organic book that you pick up pretty much has that first sentence, usually right there at the front. Organic chemistry really is the study of compounds that contain carbon. So that's almost like the textbook sentence for what organic chemistry is. But really, organic chemistry is ultimately based on carbons attached to carbons. And those carbons usually attach to hydrogens, you know, for the most part. And this is really the basis of organic chemistry, is this sort of attachment that happens here. And a couple of things about this attachment that we should be familiar with, obviously, is the carbon-hydrogen bond is nonpolar, has an electronegativity difference of like 0.4, which makes it nonpolar. Carbon-carbon bond, obviously, is nonpolar. So for the most part, you know, a lot of organic compounds are mainly nonpolar. And I say mainly nonpolar because there are organic compounds, or a lot of organic compounds, that, you know, you can almost look at them as they have kind of two parts. They have like a part that's nonpolar, but yet they do have a part that is a little bit polar. So it allows them an opportunity to interact with things like water, certain ones, and certain things cannot interact with water. But other things that we see along the way is sometimes along the way we will kind of exchange some of these hydrogens for other elements, things like oxygen, nitrogen, you know, maybe a halogen. So we can exchange some of these hydrogens along the way. And these give us what are sometimes referred to as different functional groups for organic chemistry, and gives us different molecules which have different sort of affects our abilities to interact with things like water, for example, and stuff like that. Organic chemicals affect everyday life. Their products, such as clothes, foods, medicine. And because we're really dealing with all pretty much non-metal interaction, we're dealing with covalent bonds, molecular compounds, and they really do differ a lot from obviously ionic compounds, like say sodium chloride. So organic compounds exist in these molecules that have much weaker intermolecular forces than our very strong interactions that we see in ionic compounds. So remember that when we talk about intermolecular forces, that means the force within one molecule connecting to another molecule, basically. It is that force that basically holds one molecule together with another. Those are things like hydrogen bonding. Those are things like dipole-dipole interaction. Those are things like dispersion forces. And that's different than what we see sort of in an ionic compound like salt, like sodium chloride. Those are held together by like sodium and chloride, so these electrostatic attractions. And that's basically like one ion to another ion, and that basically is what is referred to as an intramolecular force. So an intramolecular force means within a molecule. So for example, if we did have, say, two water molecules together, they would be attracted through the negative side of one oxygen to the positive side of another hydrogen in two different water molecules. That is, again, an intermolecular force. And that's different if you just had, say, one water molecule, for example. The bonds that hold the oxygen to the hydrogen, or the other oxygen to the hydrogen, or I guess the same oxygen to the other hydrogen, those are basically sharing of electrons. Covalent bonding, those are intramolecular forces. Covalent bonding or ionic bonding are intramolecular forces, and they are always much, much stronger than any intermolecular force that you have. And a simple example, just to remind you of that, is we see that when we boil water, right? When we boil water, what happens is actually this bond here between the two water molecules breaks, and we get individual water molecules that are now in the gas phase, are basically water, steam, or vapor. If it was opposite, and the intramolecular force would be weaker, when the idea here is we want to get carbon basically to four bonds, should not have any more than four bonds. And as a reminder, that carbon cannot go above the octet rule because it's in period number 2. That means it's on the second energy level and only has the p orbitals available to it and does not have d orbitals, which means it cannot ever go exception to the octet rule and go that expanded octet. So it has to do those four. Basically, it contains those, as we talked about, sort of non-polar bonds. So it contains this guy, which is non-polar, and that's because it's like 2.5 electronegativity, 2.1 difference in electronegativity. When you subtract them, it's like 0.4. 0.4 is typically the cutoff when you do the difference in electronegativity to a non-polar bond. And that's using the Pauling scale of 0 to 4, where 0 is the least electronegative, 4 is the most electronegative. And if you remember, fluorine is the most electronegative element there with a value of 4. So here's a couple of different ways that we can sort of represent these guys. Everybody will sort of have that 4, except for hydrogen. Also a reminder, hydrogen should only have 2 electrons, right? And that's because hydrogen only needs to get to helium to reach that noble gas configuration. So hydrogen, again, a very common mistake people do is this: hydrogen should never be double bonded or triple bonded. These are all incorrect. So basically hydrogen should look like this if you decide to do dots, or if you use the lines for the bonding electrons, obviously should look like this. This is the simplest organic guy you could have, which is 1 carbon and basically 4 hydrogens, and that is what is known as methane. Any questions on that there? So some more characteristics of our organic compounds are basically the idea that carbon can make multiple bonds. So carbon can form single bonds, double bonds, and triple bonds. And these give us what are sometimes referred to, these slight differences in these organic compounds are what are referred to as functional groups. And functional groups are basically the part of the organic compound which makes it is the type of organic compound you're dealing with. So what that means is if you typically have all carbon-carbon single bonds, like what we see here, this is basically a 2 carbons organic guy, which is known as ethane, and it has all carbon-carbon single bonds, and things that have all carbon-carbon single bonds are what are referred to as a group of organic compounds, which are known as alkanes. Alkanes are really important because pretty much every organic compound that you come across that you name all go back to the alkane name. So it's really the basis of pretty much how everything in organic chemistry is named is through the alkanes. And that's, again, something that has all carbon-carbon single bonds, also sometimes referred to as being a saturated hydrocarbon. Saturated hydrocarbon basically means that it has the maximum number of hydrogens that each of those carbons can have. Now, if we take the same 2 carbons and we put a double bond in it, we get another sort of functional group, which is the carbon-carbon double bond. And this guy is what is referred to as an alkene, E-N-E. So if you look at this guy here, a couple of things happen. When I put on that second bond, I need to make room for it. And in order to make room for it, I need to lose a hydrogen off of each of these carbons. Because if I just try to put the double bond in there, like right here in the center, I would then have carbon that has 5 bonds, and that is too many. So in organic chemistry, every time you put on a bond, you basically got to lose a couple of hydrogens, one from each carbon where that double bond goes. And again, it's just really making room for it. Here, if we have a carbon-carbon triple bond, that's another group of organic compounds, which are known as alkynes, Y-N-E. And we see the same thing happen as we go from here to here. We basically put on a bond. And what happened to our hydrogen count? Well, our hydrogen count was adjusted by taking off a hydrogen off of each of those. And we are left with, again, just 2 hydrogens. So in terms of the general sort of formulas, alkanes have a general formula CnH2n plus 2. What is N? N is the number of carbons. So in the case here of ethane, 2 carbons, 2 times 2 is 4, plus 2 is 6, and that's why ethane has 6 hydrogens that are around it. When we put on that double bond, as we talked about for an alkene, we lose 2 hydrogens, so it has a general formula as CnH2 times N. Looking down here, 2 for our carbons, 2 times 2 is 4 for our hydrogens, and again, that's why this guy here has 4 hydrogens. And obviously, when we get to our alkyne, it is CnH2n minus 2, again, losing 2 more hydrogens in that process. If we take 2 times 2 is 4, minus 2 is 2, gives us our 2 hydrogens that we see here. So every time we, again, kind of put on a bond, we sacrifice a couple of hydrogens along the way. Any questions on that there? The other interesting thing that you'll see, and you maybe can even see just on this sort of slide as well, is this first guy is a carbon-carbon single bonds. This is alkanes, and this is ethane, which ends in ANE, just the same. This guy in the middle is carbon-carbon double bond, which is an alkene. It is based off of ethane. It ends in ENE, and most people would call this ethene, ENE. And lastly here, our triple bond ends in YNE, and this is the common name for this, so I'll get rid of it. The non-common name, if you will, this is ethyne, YNE, and again, it matches the YNE that we see there in our triple bond. The other thing that you'll notice as well as you go through, say, organic chemistry is interesting in the sense that there are all kinds of names for the same compound. There's what is referred to as the IUPAC name, and that usually is sort of the official name when you go to name things. IUPAC, it stands for the International Union of Pure and Applied Chemistry. I'm sad I know that, but that is sort of the official name. There's some historical names that are still used a lot for certain compounds. There's common names that are used a lot for as well. So that's why, again, actually these two things that I sort of scratched out a little bit here, these guys are sort of more common names that are used for some of these compounds. And again, some are just historically been used for so long that they still use them. And, that's how come you could kind of run into, a couple of different names for the same compound. So for example, if we look at something like this guy here, this, by the way, is an alcohol because it has an OH group. Functional group for an alcohol is an OH. This is what is known as 2-propanol. That's more of the IUPAC way of naming it. This is also known as isopropyl alcohol, sort of the common name for it. It's also known as rubbing alcohol, super common name for it as well. So, even, certain things have multiple names for the exact same guy. Now, methane is a main component, obviously, of natural gas. It's basically when we light our Bunsen burners or our stove there. Ethene is the starting material in plastics. Some compounds have chains, and the guys in sort of rings form, and some are sort of straight chains. So we're looking here at two different sort of versions of a 3-carbon compound. Guy on the left is propane. Guy on the right is what is known as cyclopropane. And the difference here is this is what is referred to, this is an alkane, all carbon-carbon single bonds. And you may look over here and go, this is all carbon-carbon single bonds. This is an alkane as well. And you would be right. But because this is a ring structure, this is what is known as a cycloalkane. Basically just means that you took basically both ends and you kind of put them together. But when we do that and we kind of put them together, as we talked about before, we're going to actually need to sacrifice some hydrogens along the way. So we will lose some hydrogens. So cycloalkanes actually have the formula of CnH2 times N. Again, because they basically close up on each other, we actually end up losing a couple of hydrogens in that particular case. Cycloalkanes are really ones that, oftentimes drawn in line structure. They kind of look like geometrical symbols. Like this triangle is the same thing as this guy. And basically what that means is when you draw something in line structure, every time there's kind of a point or an end to the line, it represents a carbon. So that would be a carbon there, that would be a carbon there, and that would be a carbon there. And because carbon needs 4 bonds, this carbon has 2 lines coming in, which means technically it's got 2 bonds of hydrogen. Same thing here. It's got 2 lines coming in, which means it's got 2 hydrogens and 2 more hydrogens. Although in line structure, we typically do not draw the carbons or the hydrogens. It's really just lines. Just like we can have a square, which represents cyclobutane. Again, each of these guys would be a carbon, and there would be the appropriate amount of hydrogens coming out on each of these sides. We could also draw line structures for guys that are not in a ring type formula, like what we have here. We could draw this right here. would represent 1 carbon, 2 carbons, 3 carbons, 4 carbons. So everywhere sort of ends as a carbon. This would have 3 hydrogens. This guy would have 2 hydrogens. This guy would have 2 hydrogens, and this guy would have 3 hydrogens. So again, this would represent basically C4H10 that's happening in this case. If we want to draw propane, it would look something like this. Again, 1 carbon, 2 carbons, and 3 carbons. Again, you don't usually draw the circles, but that would be there. And again, since each of these are carbons, the guy in the middle would have 2 hydrogens coming out. Again, because there's 2 lines coming in. Guys at the end would need 3 hydrogens to get the 4 bonds. And again, that's what we see in the tower picture that is there as well. So we can write these things in sort of line structures, which looks like this. Also, by the way, if you have just a line and line structure just coming out, you may be wondering, like, what is at the end of the line? Well, if there's nothing drawn there, it's assumed to be a carbon with the appropriate number of hydrogens. So, if you had something drawn like this would be assumed to be like a CH3, just like at the end here would be assumed to be a CH3, just like at this end would be a CH3. And this guy right here would actually be a CH2, and this guy would actually be a CH that is there as well. So line structures are oftentimes used a lot in chemistry, and sometimes people get confused by, hey, there's a line, I'm not sure what goes there. Again, if nothing is there, it's going to be that carbon with 3 hydrogens. If they want something there, they will write it in. So they'll put something like Cl if they do want, obviously, something to go into there. Any questions on that there? So organic compounds may, as I mentioned earlier, contain other guys besides carbons and hydrogens. Again, a lot of times some of the hydrogens get sort of replaced along the way, and we get some other guys involved. Very common nitrogen oxygens involved. A lot of times the halogens are involved. So these are common sort of guys that will sort of separate out and basically make some bonds in there. And depending on sort of what binds in and what doesn't bind in, we do get some different sort of um, functional groups that occur. If we swap out a hydrogen for some oxygens, we can get several different functional groups that will occur. Here's just a table of some common type of bonding that we see happening in organic molecules. Things like hydrogen, again, should be at the end, never in the middle, only 1 line. This is a very important. Our carbon should never go over that 4 sort of bonds. Nitrogen, oftentimes nitrogen containing guys, for example, things that have this group here, these are what are referred to as an amine, and that's a nitrogen containing group. You could also have a nitrogen containing group that has a carbon oxygen double bond like this. This is what is referred to as an amide. And these nitrogen groups are kind of really based off of almost like ammonia, which looks like this. So they look very similar. They got this nitrogen and a hydrogen bond, which means they can participate in hydrogen bonding. Remember, to participate in hydrogen bonding, in a bond between hydrogen, nitrogen, oxygen, or fluorine, in order for that to do it. A lot of times, carbon will do some double bonding to the oxygen, and this creates what is referred to as a carbonyl group. And this is also a polar group. The bottom part is more positive, top part is more negative, and that's really important for a lot of sort of reactions that occur and how they sort of occur as well. A lot of times we'll find our halogens on the end there, and again, they'll have a lot of non-bonding electrons sort of happening. The most common multiple bond between carbon and some other atom is that carbon-oxygen double bond, as I just mentioned, which is known as that carbonyl group. And again, by substituting out some of those hydrogens from these other guys, as I mentioned earlier, we do get this different functional group here. And again, in the case of OH, that is what makes it an alcohol. Here we have this part actually is a functional group. And that involves a carbon-oxygen double bond with a hydrogen at the end. And this is a group of organic guys which are known as aldehydes. And has that sort of functional group that occurs. And if you look at sort of the names here, if you remember, we saw earlier the one carbon simplest organic compound you could have is methane. This is a one carbon alcohol. And again, you can kind of see where the name comes from. Methane, methanol, OL, because it's a alcohol, it ends in OL. This is an aldehyde. This is actually the common name for it, which is formaldehyde. The IUPAC sort of official name for it is what is known as methanal, AL. Again, because it has one carbon, as I mentioned earlier, and as you will see, everybody comes back to sort of the alkane, which is this guy. And again, based off of methane, the way we officially name aldehydes is put an AL at the end of it, and this is known as methanal in terms of it. Any questions on that there? Now, obviously in organic chemistry, there's multiple ways that we can represent sort of formulas and stuff like that, some of which we've talked about a little bit here, but let's talk about some of the major ones. One is a condensed formula, and one is sort of what is referred to as an expanded structural formula. So these are the two examples of it. This is what is sometimes referred to as the expanded structural formula. This is really a condensed formula, and a lot of times people will write it more like this with the actual dashes in it, which is very common. And this is what is referred to as the condensed formula. What is the difference between them? Well, the difference is in sort of the expanded, you basically draw out the hydrogen bonds. And sort of the condensed one, you don't really draw out the hydrogen bonds. You just kind of do them as groups of like CH3, CH2, CH2, and that's what we see here, CH3, CH2, CH2, CH3. And obviously our line structure, which would have 4 carbons, would look something like this. Again, 1, 2, 3, 4. So that is the same thing as this guy, which is the same thing as this guy. Again, this would be our line structure, our line formula. This would be our expanded structural formula where all the hydrogens are drawn out. And this would be our condensed formula as well. Any questions on that there? So you may be wondering why this is sort of zigzag like that. And that classic sort of zigzag comes from, as we'll talk about as well, the geometry that's happening here. We basically have 4 electron pairs and 4 bonds, and that's tetrahedral. So all these guys here in alkanes have that tetrahedral geometry, which gives it that classic, what is sometimes referred to as zigzag shape that we see in organic compounds. Now, sometimes we will emphasize some bonding here. This is what is sometimes referred to as a group that's attached. Also what is sometimes referred to as being a branch chain. And what is a branch chain versus sort of a straight chain? Well, a straight chain is pretty much what it sounds like. You just got like a straight row of carbons and hydrogens, sort of bonded together. A branch chain basically means very much like what it sounds like. There's kind of a main part to it, like in a tree, right? There's the main part. And off of the main part, there's some other things attached, and stuff like that, like branches on a tree. So that's what is sometimes referred to as the branch chain versus, say, a straight chain molecule. Now, sometimes we do get a big run of sort of repeatable units. So sometimes we'll do some different ways to represent our organic guys. This is basically a CH2 unit followed by another CH2 unit. So sort of a shorthand is we'll put the CH2 in parentheses, put a little 2 on the bottom, and that indicates that we have 2 of those guys kind of in a row. Again, if it's on the outside, you can kind of do that as well to represent that. So sometimes you'll come across things where you'll have like a CH2 to the 8, for example, something like this. And that basically means that, you have the CH2 unit in between those 2 guys, 8 of them in a row, which means technically this guy has 1 carbon, 8 more carbons is 9 carbons, and 1 more is 10 carbons. So instead of drawing out all 10 carbons all in a row, we kind of do this sort of shorthand where we take those units that are in the middle and put parentheses around them and how many we have. Any questions on that there? Now we have our skeletal structure, which again is basically kind of like line structure, like I talked about. And the idea behind everything when we're drawing organic compounds is the idea of carbon. And really, the goal is to really get carbon to 4 bonds. That's sort of the goal. And that's a good thing to keep in mind as you go through it. And that's how you know when you're drawing something, as we'll do a little bit later on. How do you know how many sort of hydrogens you should put in there or what else goes in there? And it's really based on that very simple concept that we want to get carbon to basically 4 bonds. And to do that, basically, if nothing else is there or told that something else is there, it basically is going to be just hydrogens that are going to be present in this particular case. So again, here in this sort of ring structure, this would be more of the expanded structure sort of drawn, and most of the time people will never ever draw it like this. Most of the time you're looking at it drawn like this in sort of line structure. And again, at each of these points is a carbon with the appropriate number of hydrogens. So for example, this guy that should have 2 hydrogens, 2 hydrogens, 2 hydrogens, 2 hydrogens, 2 hydrogens, and 2 hydrogens. This would be more of the condensed formula over here. This would be our line structure. And this guy is again drawn here. You may count up the carbons. This is basically 6 carbons in a ring structure. This is what is known as cyclohexane. Cyclo because it's a ring structure. Hexane means 6. There's 6 carbons involved. And again, it will have 2 less hydrogens than basically hexane, which would be the straight chain version of it. Again, if we have some type of kind of ring structure here, we could just draw out our hydrogens. In the case of sort of condensed formula, we usually won't draw the bond between the OH. But you remember that when you do see this, this is an OH bond, which means it is a polar bond, just like it is, say, in water. And again, the presence of something, say, like this, can give this compound some, say, solubility, for example, with water because it has a way to hydrogen bond with it. Even though a vast majority of the compound there is nonpolar, a lot of organic groups will share this sort of common feature of it will have sort of a spot where it has that ability to do things like hydrogen bond and stuff like that. Now, as you'll learn as well, that and it really is dependent on sort of how big this part of it is, how big the nonpolar part is. You can have an organic compound that has a very big nonpolar part, very small polar part, and it really won't be able to do much with water because it's too big. The other guys kind of get in the way of that ability to hydrogen bond. And that does bring us up to sort of functional groups in organic chemistry. And as I mentioned, these functional groups are really, the part of the organic molecule that makes it a certain class of organic compounds. So as we talked about a few of them here, as we just went through some of them, for example, again, that carbon-carbon single bond being an alkane, carbon-carbon double bond being an alkene, carbon-carbon triple bond being an alkyne. We saw the OH bond, which is an alcohol. We saw the aldehyde, I think, in one of those pictures there. Also saw the NH2, which is an amine. We talked about the amide, which looks like this. So you have a lot of these sort of little parts of these organic compounds. And again, depending on sort of what is present, you do get a different sort of class of organic compound, which may have obviously a different name. It'll have some different properties depending on sort of what is attached along the way. So hydrocarbons, as I mentioned before, are pretty much like the name implies. They are compounds that basically contain only carbons and hydrogens, hence the name hydrocarbons. Alkanes, again, having that single bond, carbon-carbon, alkenes, carbon-carbon double bond, carbon-carbon triple bond happening there with our alkynes. Aromatic guys are guys that basically contain benzene, and benzene is a 6-member ring, kind of like cyclohexane we just saw, but it contains 3 double bonds. So it looks something like that. You could have a resonance structure where the double bonds are on the other side, or sometimes people will, for benzene, just sort of draw a circle in there to indicate that those double bond electrons are moving around and they're delocalized. Those are all benzene structures, and that's what makes something aromatic. It's basically 6 carbons and 6 hydrogens is the formula here. Because it has those double bonds in there, there's only 1 hydrogen happening at each of these carbons. And that again is our benzene. Now, again, pretty much everybody boils down to our alkanes in terms of naming and stuff like that. And basically, it is important to learn sort of the names of these first 10 alkanes, for example. They can be very helpful. So if we look at alkanes, and again, alkanes having those structures like we talked about of CnH2n plus 2, while our alkenes have CnH2n, and our alkynes have CnH2n minus 2. That means that the very first alkane that we talked about is CH4, which is methane. If I end up with 2 carbons, 2 times 2 is 4, plus 2 is 6 hydrogens. That is ethane. 3 carbons, which means 3 times 2 is 6, plus 2 is 8 hydrogens. That is propane, ANE. 4 carbons means 8 plus 2 is 10, would give me butane, ANE. 5 carbons, which would give me 12 hydrogens, is pentane, ANE. 6 carbons, giving me 14 hydrogens, is hexane. 7 carbons, giving me 16 hydrogens, is heptane. 8 carbons, giving me 18 hydrogens, is octane. Like fill up your car. C9H20 is nonane. And C10H22 is decane. You can see that they all end in ANE, just like our alkane ends in ANE. These first 10 are really important, again, to understand their names, their formulas, because absolutely everything else that we kind of go across and we name basically will be based off of these first 10 names. So really important to kind of know those guys. Everything just goes back to those guys' names and stuff like that. So here's a table, similar one I think in your book, but some of the different functional groups that we talked about. So again, sort of if we kind of look through some of these guys that we talked about, we have our carbon-carbon double bond, which is our alkene. Here's really our carbon-carbon single bond with this our alkane. Go to a triple bond, we have an alkyne. Aromatic compound, again, this whole thing here is benzene, so that's our benzene ring. So it does need to kind of contain those guys. What is sometimes referred to as an alkyl halide is really just an alkane with a halide, means halogen. So we see a halogen attached there. An alcohol, as we talked about, has that OH group. An ether has a really carbon, oxygen, carbon type group. So you can see carbon, oxygen, carbon connection in a row. Basically, the R there, by the way, does represent, R is a carbon containing group. Looking over here at the amine is that nitrogen containing group that we talked about. Again, it has this sort of group there. A thiol, it has a SH group, so a sulfur containing group. Thiols, are also on amino acids. They're the guys who make like disulfide bridges when they come together. You get a couple of thiols kind of coming together. Take out the H2 and basically get your disulfide bond that occurs. And again, cysteine, for example, is an amino acid that has that. As I talked about, a lot of organic guys will have this carbonyl group, and this is a polar group. Again, this being more positive based on electronegativity, this being more negative. That allows certain interactions to actually occur here at the carbon-oxygen double bond. So it's kind of an important group, and there's a number of organic guys that do have that group part of it, including our aldehyde, which has our carbonyl group here, but this whole thing right here with the hydrogen is the functional group for an aldehyde. Ketone is basically 3 carbons in a row with the double bonded oxygen in the middle. And again, a ketone has really that 3 carbon run with the double bond happening there in the middle. Carboxylic acid, right about there, is the functional group. And again, has a carbon-oxygen double bond and that OH group. You may be familiar with this guy here. A lot of weak acids are carboxylic acids. That is CH3COOH. That is acetic acid. That is also 2 carbons, which is based off of ethane, also known as ethanoic acid, also known as basically the major component of vinegar as well. So a lot of these guys have that carboxylic acid group, and this is the carboxylic acid group right here, and it has a lot of times written like that. So when you see that COOH, it is really this organic group, that carboxylic acid group that is present right there. Not to be confused with an ester. Ester also has a carboxylic acid group, but it has no hydrogen is connected to a carbon. So this is an ester, basically made from a carboxylic acid and an alcohol there. Will get you your ester. And again, here, there's our amide, which is our basically carbon-oxygen double bond with our nitrogen-hydrogen for our amide group that is present there. So, depending on sort of what is present in terms of the bonds that are there as to sort of what chemistry that will happen, will things be soluble? Will things not be soluble? This is the amide group right there. And again, this guy has a polar sort of part there. This is also polar. So it does give amides some polarity or solubility in things like water because of those abilities to interact. Any questions on that there? Okay, so I think that's enough torture of lecturing, I think, for now. And we'll save us something to talk about on Thursday, which will be our last day of lecture. Remember that our final is, we actually have 2 finals next week. So we have one that is the lab final, which is, sort of probably not the hardest of the two, I imagine, but you know, kind of based on some of the calculations and stuff that we did sort of in lab, all the way through things like safety and stuff like that. So, you know, those type of things will be included in there. And then I believe our lecture final, the real final, I guess, will be on Thursday of next week. So we got one more day. So we'll finish up some more of this organic stuff, I think. So that way at least you've seen it. And other than that, you do have, I think,